All right, good afternoon. I wanted to walk through a program for a paper I'm looking to publish and wanted to give a little bit of idea about the coding complexity and how we can use reproducible research strategies for deep learning. So to start, I'm going to open up a couple different things. I'll show what the data looks like. As you can see, I'm using R to do the deep learning. It's configured so that it goes out and calls TensorFlow through the articulate package. So I'm going to load some data. This is looking at our raw image data, create a couple of helper functions to show what the images look like. One of the things you'll see here is we need to do some minor image adjustments. So I'm going to load the raw images as well as the post-processed images that accomplish something that's known as window and leveling within sort of the radiology speak. So it's going to take a few moments. It's a large data file, several gigabytes worth of data. What we're looking to do is use a convolutional neural network to predict what is known as background parenchymal uptake. And BPU is a radiologist's interpretation of how much tracer is visible within the breast tissue. So it ranges from photopenic to minimal to mild to moderate and marked uptake. And that's our training task. So one of the things we want to do is create a visualization of that. So we can start with an example. This is one of the cases. It's photopenic. You can see how the brightness changes ever so slightly between the images. What I'm doing is truncating off the top if it's, say, brighter than white, and also leveling out the bottom to make the black a little bit deeper. So there's an example of a photopenic image. We can look at another one. This is a different view. You can see that what is viewed as the photopenic is the dark area within the black tissue. We can go up through the scale, minimal to mild to moderate, and then ultimately to marked. And so you can see as the pattern increases, the overall brightness of the breast tissue increases. And this image shows what is a radial label. So outside the breast, there is a marker to be able to tell the radiologist whether it's the left or the right breast. One of the things we encountered early is, what happens if a lesion's present. So the reason the exam is done is that it's believed that the breast cancer risk is related to how concentrated the uptake is. And so this very bright region represents a high metabolically active region of breast tissue. One thing we noticed going in, you'll see a lot of pictures of BPU in the literature. The images look lovely. Some of these, when I view them, we get a single bright pixel. It's believed to be just an artifact within the DICOM file. What my leveling does is limit this so that the scaled image then works on a more reasonable grayscale structure. And that improved training a reasonable amount. Now, one of the next stages is once we do all of that, I have a couple programs. This one loads the normalized data. You can see that we've broken our data down to a training and testing data. All the interface to my modeling comes from the TFRUNS package within R. This package allows you to do two things. One is a training run where you can call a program that defines, say, the architecture grid you're looking to do and specify a single set of values. A tuning run looks very similar. The difference here is that you're able to pass in combinations of values to be used to form a grid search, and then you can sample from that grid a certain proportion. Now, where this program is now, it's gone through multiple iterations. So we've trained, we've learned, we've narrowed, and we're down to really a small set. When we first started off, we had a much larger array as well as a different sampling fraction. That skeleton looks like this. It's a very efficient coding framework. So what you end up doing is you define variables that you want to be passed and permuted from model to model. You go through, you make the definitions, you can specify default values if you'd like. I'm passing through values and try to fully specify the parameters just to keep it clear in my mind what the individual model was doing. Go through, you load the data, you do some different counts to set up the Keras model architecture. For those that are used to fitting Keras within Python or native Python, you would see like a model dot, and then you specify the sort of the architecture being applied. Within R, it looks very similar. You define a Keras model as sequential, and then you use this piping layout to basically take the prior iteration and add to it. You can do this a variety of ways. I did learn, while it looks redundant, to keep specifying model. It allows me to easily do things like some if-then logic and piece together a model without any complicated command line parsing within R. You go through here, you can do all the normal things you can in Python. One of the things we've done here is to do some of the callback functions, trying to save the best epoch. Turns out I really don't like using that, but I keep it just in case. We can do early stopping, and then also this reduced learning rate on plateau. And this reduced learning rate on plateau is actually very helpful, particularly if models are having a hard time to get converged. You can start with maybe a more aggressive value for the learning rate and then really slow it down quickly by combinations of the factor variable as well as the patience. Patience here is how many epochs does it wait before reducing the learning rate. So we can do this. We go through a couple different things. I have it set up to do either just split sample validation or possibly data augmentation, where we can use a validation image generator. You know, it turns out that I didn't have a lot of great luck with the image augmentation. I think where I need to look a bit more is potentially turning down some of the aggressiveness of some of the image augmentation. You go through, compile the model, and you fit it. And one of the last steps is you can check the sort of the model performance on your test data. All of that, when it runs, it creates an environment that allows you to store all of the data from run to run. So one of the things I want to do here, we already have, we'll reload some of this. Actually, I'll just go here. I'll show you the output. So this list runs, goes out, all the models are saved underneath the runs directory. Each one is timestamped, dated. It stores the programming code, the final output, all the stuff you would want. And we can do normal R functions now that it's been pulled into a data frame. So we can sort it. And one of the things I'll do is I'll open up this just to show. This is one of the final candidate models in terms of architecture. You can see there was a little bit of a blip here, and so one of the things I set out to do was to retrain it, allowing a little additional time as well as adjusting the learning rate on plateau. And so our final resulting model was this one, where you can see that it gets through this rough patch and then settles back down and performance looks right. And so at this point it terminated due to loss of, or no longer observing performance improvement. Nice thing, I'm using R is it's a familiar language to me, and so I can do very easy things such as save those model objects and then be able to comment those out. You can go through at this point, now that I've saved my final 5-category model, I can go through and do some different performance evaluations. So in this case, I'm looking at, predicting, deriving some variables. A subtle change I've commented on in prior videos, because it's natively using Python behind the scenes, you come back with arrays often indexed from 0 to, say, k minus 1. R will treat it 1 to k, so you do have to be aware and do some minor shifts as necessary. Then you go through, I'm doing a couple of derivations, some binary classifications of BPU, giving some labels to things. I then also create a couple tall data objects that I can use for plotting purposes, as well as deriving a patient level variable representation for this. And in terms of the radiologic task, each breast is examined. There are up to 4 images per breast included, and the model that we fit treated each image independently. At this point, I can save out all these data objects, so you need to utilize a GPU for all the learning. Even the prediction objects or the prediction methods require a tremendous amount of computing capacity. But once you have those predictions, you can save them, and then you can do relatively routine things. I'm generating a report here, a markdown object. I use what I like to call object-oriented markdown. I try to keep within my markdown object minimal data processing, data derivations. I put all that within the analysis program. And then what I'm largely doing is doing simple calls and reports based on defined objects. So in doing so, it keeps my markdown very clean, and results come out. And these are some of the results we have. I won't go into much detail, but that's what we have. That's the programming environment. That's how we're working towards reproducible research. And I look forward to getting the paper published. Thank you. Bye-bye.